Hello, today we are looking at section 10.9, Taylor series and Maclaurin series. They really come from the same place, but Maclaurin series are centered at 0, and we'll discuss what that means in a few minutes. Students will express a function as a Taylor series or Maclaurin series, determine the convergence of a Taylor series or Maclaurin series, and find a Taylor or Maclaurin series expansions. So how do we find a polynomial representation of functions? And that's with the two series above. So we can use either a Taylor series or that Maclaurin series. And I know that doesn't mean much to you right now, but we can take any function anywhere, sine, cosine, tangent, e to the x, natural log of x, and rewrite it as a polynomial. And these series allow us to do that. So your Taylor series is this formula here. F of c, f prime of c times x minus c. What I want you to do is notice the pattern. It's the nth power derivative, n factorial, n as an exponent, and x minus c inside. So the x minus c, I want you to remember a parabola, right? That's a parabola. If I do y equals x minus 2 squared, that's a parabola that is shifted right 2. So this x minus c, all that does is shift our polynomial. When we have a Maclaurin series, those are centered at x equals 0. So those are a very special subset where we're centered at 0. And here are the short forms of those terms. So we have this piece and this piece. So let's see what this looks like. Assuming that f of x equals e to the x can be represented by a power series in x, find its Maclaurin series. So I'm going to scooch up here a little bit. We need a list of the derivatives, and we're going to put it into that form. So I'm going to start with f of x is equal to e to the x. So we want to take derivatives so that we can use that Taylor series formula. So the first derivative of e to the x is e to the x. The second derivative is still e to the x. And the third derivative is still e to the x. So then where are we going to evaluate all these? Because it's a Maclaurin series, we're going to evaluate them when x is equal to 0. So we want to put 0 in place of x for all these derivatives. All of these will be equal to 1. Now, we're going to start with the formula. So it's f of 0. Let's give ourselves some space here. Plus f prime of 0, x to the first over 1 factorial, plus the second derivative at 0, x squared over 2 factorial, plus the third derivative at 0, x cubed over 3 factorial. And you get the idea from there. So f of 0 is 1. This is 1 x to the first over 1 factorial, plus 1 x squared over 2 factorial, plus 1 x cubed over 3 factorial. And then you would want to ask yourself, can you come up with the overall formula? And the answer is yes, we can. This would be n factorial in the denominator and x to the n in the numerator. I put this series notation in the front. This starts at 0 and goes to infinity. So this piece up here is the expansion. This is the series representation. And you can replace e to the x with all of that. So just kind of keep all this in mind. F of x equals e to the x is the same thing as 1 plus x squared over 2 factorial plus x cubed over 3 factorial, dot, 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 which is the same thing as the series representation like this. I gave you in class a red piece of paper with the series on it. You're going to consult that. All right, convergence of a Taylor series. This tells you where it converges. I don't want to have to prove that. You're not going to have to prove that in the EP exam. So we're just going to go with this. So on that red piece of paper that I gave you, the right-hand column also lists where it converges. It's either between 1 and -1, or it's for all values of x. So just consult that paper each time. So we're not going to show this. So use red formula sheet. But I do want to show you, I want to show you what this looks like. So I'm going to pause my video and hop over to Desmos. All right, so I've popped over to Desmos here, and just to give you a quick idea, this is something that I Googled and it came up with this formula for me, but basically these are the derivatives. So those are the terms for the Taylor polynomial, and down here is where they've substituted them all to come up with what's going on. So this red curve that we have right now, this is that series expansion. And what are we comparing it to? We're comparing it to e to the x, and we're centered around 0. So that blue curve has actually lined up exactly with the red curve as we come over here to the right. And I think they line up all the way up there. Over here around -4, -3, they start to not be a good match, but that's where they're a good match. If I look at number 3 here, this is the series representation, and this is what we just came up with. We have x to the n over n factorial. I'm going to choose this with up to 20 terms. So I'm going to turn this one on as well. So the purple curve only showed up over here on the left-hand side. So that matches my e to the x a little bit further, the blue curve. But if you look, all 3 of them are really one on top of another over here, which makes it kind of interesting. And I don't think I can change that. So there's the purple one. That red one's on top, so it's just tough to see. Maybe if I make it thicker. There we go. Now you can see the purple one. And then the blue one as well. We'll make it look like this. There we go. So it looks kind of goofy over here on the right-hand side, but you can see that all 3 are plotted together. Remember, we did this as a Maclaurin series. So we want it to be matched up around 0, and indeed it is. And if we zoom out even further, you can see to the left, they start to diverge a little bit. They don't all match, but to the right, they're still a pretty good match. So obviously, the more terms you have, right, the more k values you have, the higher k goes, the more terms you have in the series, and the higher your polynomial goes, the more terms you'll have as well. And then they will be an even better match to e to the x. So I think that's pretty cool. So there you go, just showing you that all 3 representations do give you the same picture. That's what I really wanted to show you in Desmos. Example 2, we said we're not going to worry about. You can look that up in the book if you want to. Example 3, before the next video starts, we're going to start with that Maclaurin expansion. So what you need to do is look at your function, which is f of x equals sine of x. And then you want to look at some derivatives. So the first derivative is cosine of x. The second derivative is negative sine of x. The third derivative is negative cosine of x. And because this is Maclaurin, these are all centered at 0. So x equals 0. So sine of 0 is 0. Cosine of 0 is 1. Sine of 0 is 0. And negative cosine of 0 is negative 1. And then I think my other video picks up in here on how to put it all together. So good luck with these. They're tedious, but it's just a formula that you use over and over and over again. They're pretty good.